Okay, this is a problem about general energy transfer and energy balance in systems. It shows a pump that is pumping water from a lower reservoir lake to a higher reservoir, and the input power to the pump is 20 kilowatts. And the difference in the height of the two reservoirs, the surface of the two reservoirs, is 45 meters, and the volumetric flow rate through the pump is 0.03 meters cubed per second. We have to determine the amount of mechanical power that is basically wasted by being converted to thermal energy due to frictional effects. So we can look at there are different ways of solving this problem, different approaches, but we can look at the general form of the first law for this system and try to simplify it. This is the method that I recommend. So starting from this equation, Q dot in minus Q dot out plus W dot in minus W dot out plus E dot in minus E dot out is equal to change in rate of energy of the system. Okay, to simplify this, we have to have a good control volume selected, right? So what seems to be reasonable is a control volume that looks like this. So it includes the pump and the two reservoirs. So basically this will be our input or inlet, and that is our outlet. So 0.1 is inlet, 0.2 is an outlet, right? Now, assumptions. These are very important. It's water, it's ambient temperature. We don't expect any change in temperature because of this process. We can say that temperature anywhere remains constant. That's a reasonable assumption. Based on that, we can say because temperature remains constant, we can use it for simplifying two terms or more than two terms in this equation. So we don't expect any change in internal energy. We'll talk about that later. Also, because there is no temperature difference between the water and the ambient, this can be interpreted as no heat transfer rate. So the first one is no change in internal energy, and the second one, no heat transfer rate. All right. So let me go to the equation here, and based on no temperature difference between the water and the ambient and Q dot was 0, I can scratch both of these terms. So our equation is simplified now. Let's go further. Let's look at the third term here. E dot in minus E dot out. This is the energy uh, entered, energy entered by mass. That's the meaning of the term. And E dot out is energy exited by mass. This needs a little bit of attention. If you look at this, it looks like it's a flow system. The water is flowing from here through the pump to the upper reservoir. But based on some assumptions, we can simplify it actually. What is that assumption? The assumption is that the reservoirs are large enough or very large. What does that mean? When the reservoirs are very large, it means that surface level remains unchanged. How does that help us? So if you look at the control volume one more time, here and here, when this level or the value of Z doesn't change, we can assume actually there is no energy coming in or crossing the boundaries of the control volume here or crossing out of the energy volume. This is to show that mass is not crossing the boundary. So when mass is not crossing the boundary, it means energy with mass is not crossing the boundary. So I can scratch both of these terms. All right. So our final form of the equation is just simply W dot in minus W dot out is equal to change in energy of the system. This is total energy of the system. So total energy of the system in rate form is consisted of change in kinetic energy of the system plus change in potential energy of the system plus change in microscopic forms of the energy or internal energy of the system. The delta sign is to show the difference between initial and final state. So let's go back to this assumption here. Temperature remains constant. Therefore, internal energy remains unchanged, can be scratched. Let's talk about changing kinetic energy. The dot sign, of course, is to show that it's rate form. It is joules per second or watts or kilowatt. This, by definition, is mass or m dot times 1/2 of V final V2 squared minus V1 squared. V at inlet, V final, and V initial. So back to this assumption that the reservoirs are very large, we can conclude that both velocities are zero. As a result, change in kinetic energy is zero. Our equation is getting simpler and simpler. So finally we have W dot in minus W dot out. From delta E dot of the system, we just have delta potential energy, the rate for potential energy change. This is a simplified equation. Looks like we have enough information to solve this. So delta potential energy in rate form is m dot G delta H, which in our case is m dot G H2 minus H1, or actually Z2 minus Z1, same thing, Z2 minus Z1. We can calculate m dot now, or multiply it by all the terms later. So m dot is density of water times V dot, which is the volumetric flow rate. Density of water, it is safe to assume it's 1,000 kilograms per meters cubed multiplied by V dot given as 0.03 meters cubed per second. The answer is going to be 30 kilograms per second. That's the mass flow. And as a result, our delta potential energy, rate of change of potential energy, will be 30 times 9.8 times delta Z, which is 45. The answer is 13,230 watts or joules per second, or 13.23 kilowatts. Now let's look at this equation. You know the right hand side, the left hand side is the amount of power into the system and the amount of power out of the system. The amount of power into the system is the only source of power into the system is the pump, and that's 20 kilowatts. And the power out of the system is basically W dot loss that has turned into thermal energy. This should be equal to the right hand side, which was 13.23, and W dot loss is 6.77 kilowatts. That's the amount of power lost because of this system, because of pumping water from a lower reservoir to a high reservoir at the given volumetric flow rate.